Okay, so thank you for the introduction. It's a pleasure for me to be able to talk at this conference. I talk, as you said, about a joint work with the previous speakers, and is a work on algebraic geometric codes from a certain maximal curve. Let me just start with a super short introduction on the basics, just to fix some notation. So an NKDQ code C will be a k-dimensional subspace of fq to the n. Fq is the finite field with q elements, q a prime power, and d is the minimum distance of the code. Here we are considering the Hamming distance, which is the number of positions in which two vectors differ. And the minimum distance, of course, is the minimum among all the distances between two vectors of the code. So the minimum distance is related to the error correcting capability of the code as follows. Therefore, in coding theory, we look for codes and family of codes with good parameters, namely with large minimum distance, so that we can correct many errors. So there are many constructions, and in 1981, Goppa discovered that we can also construct linear codes from algebraic geometric codes, algebraic curves, sorry. And the relevance of this construction is that we can actually get for free lower bound on the minimum distance, which is in the general setting an hard task. So let me fix some notation about algebraic curves. An algebraic curve X will be a projective, absolutely reducible and non-singular algebraic variety of dimension 1, and it will be embedded in an r-dimensional projective space over the field K. It will be an algebraic closure of our finite field Fq. Now, the function field associated to a curve X is the field whose elements are of this form, namely f plus I over g plus I, with I the ideal of all the polynomials vanishing on X, and f and g homogeneous polynomials of the same degree. So if we are in PG RK, they will be with r plus 1 variables. So if we further require that f and g also have coefficient in Fq, we will get the Fq rational function field Fq of X. Now a divisor will be just a formal sum of a finite number of points, namely it will be something of this form, with np an integer which is 0 up to a finite number of points. And finally, we need the definition of Riemann-Roch space, which is a vector space that we can associate to a divisor D, and whose non-zero elements are those Fq rational function alpha on X, which satisfies this condition that impose some constraints on the zeros and the divisor and the poles of the function alpha. Now, if you fix a curve, an algebraic curve X of genus G, and n Fq rational points P1, Pn, and a further Fq rational points P, which is distinct from the previous ones, you define divisors D and G as in the slide. Then you can define two linear codes as follows: CLDG, whose elements are the n-dimensional vectors with coordinates the evaluation at the points prescribed by the divisor D of the functions which belongs to the Riemann-Roch space associated to the divisor G. And of course, we can also define the dual of this code, which can also be obtained by other ways with the differential on the curves, but we are not interested in this case. So this is not the most general framework, since we are making strong assumptions on the divisors G, but that's what we are interested in this talk. And so we have the particular case of 1 point AG codes or Goppa codes, and 1 point because G, the divisor G, as a support just 1 point. Now, as I told you before, the relevance of Goppa's construction is that we can get for free a lower bound on the minimum distance, and indeed we have this these inequalities. Namely, we have that the dimension is as follows, and the minimum distance is at least n minus n. And also for the dual code, we have an inequality, a lower bound on the minimum distance. In both cases, we can see, if we look at the singleton defect, that is bounded above from the genus, and therefore the relative singleton defect is bounded by the genus over n. And therefore, it's clear that since we are looking for small relative singleton defect, it's good if we have many rational points on the curve. And indeed, in the literature, many attention is posed to maximal curves, namely those curves with, which have the maximum possible number of rational points among those of a fixed genus G. Another tool which is fundamental when dealing with one-point AG codes is the Weierstrass semigroup at the point P, at some point P, because using this, the knowledge of the Weierstrass semigroup can lead to an improvement on the Goppas bound on the minimum distance. So I just recall the definition as numerical semigroup S is a subset of the non-negative integers with finite complement and its elements, and which is closed under addition. Its elements are called the non-gaps, and the elements which are non-gaps, which are not non-gaps, are called the gaps. And finally, the genus is the number of gaps of the semigroup, namely the cardinality of the complement of S over the natural numbers. Now, given an algebraic curve X and a point P, you can attach a numerical semigroup at this pair, the curve and the point, whose non-gaps are those non-negative integers n, such that there exists an FQ rational function f on X with pole divisor, with principal divisor, with pole divisor precisely n times p. Now, the celebrated Weierstrass gap theorem tells us that for a curve of genus greater than 0 and a point p on X, we have that the genus of the Weierstrass semigroup is precisely the genus of the curve. And moreover, we have that the structure of the Weierstrass semigroup is the same for all but a finite number of points, which are indeed called Weierstrass points of the curve. Now, in our work, we computed the Weierstrass semigroup at some points of the GK maximal curve, and we used that knowledge to construct AG codes from FQ to the 7 but not FQ rational points on this curve, and we used the Feng-Rao construction to get an improvement on the Goppas bound. Now, the GK curve is the non-singular curve defined by these two affine equations. It has this genus and that many rational points, and its relevance is that it is maximal over the field FQ to the 6, and it was the first example of a maximal curve which is not covered by the Hermitian curve. So many people studied this curve and algebraic geometric codes from the GK curves. We are not the first one. And the situation is as follows, and also, of course, the Weierstrass semigroups. The situation is as follows. So in 2009, introducing the curve, Giulietti-Korchmàros also provided a description of the Weierstrass semigroup at points which are FQ squared rational. And in this case, we can see that there are 3 generators on a minimal set. In 2011, Dursma made a conjecture about the Weierstrass semigroup at points which are FQ to the 6 but not FQ squared rational. And in this case, we can see a linear number of generators, linear with respect to the size of the field. And the conjecture was settled down by Belen and Montanucci in 2018. And in this same paper, they also provided a description of the gap set for the Weierstrass semigroups at the remaining points. But here they didn't provide a a set of generators, and they left that as an open problem. And here the main difficulty is from the fact that the set of a minimal set of generator is not anymore linear on the sides of the field. Indeed, and this is our main contribution, we can see that a minimal set of generators is provided by this S, this set S, which has sides quadratic, a quadratic side on the field sides. So just give a sketch of the proof. A key ingredient is this lemma from Bell and Montanucci, which provides, as I said, a description of the gap set for the Weierstrass semigroup at these points. I'm not going into the details, but the point is that every time you have a gap, then you can write it down in this way with all these constraints. And if for a non-negative integer you cannot write it this way, then it can be a gap, and therefore it will be an element of your Weierstrass semigroup. Now, if we denote by T the semigroup generated by our set of generators, we have to prove that it is contained in the Weierstrass semigroup, and it has the genus of the GK curve. In this case, indeed, we have that each gap of the Weierstrass semigroup is also a gap of T, but they have the same number of gaps because it is, for both of them, the genus of the GK curve. Now, the first task requires you to write each generator X of S as in the previous slide, and you can reach a contradiction. Therefore, it is not a gap and must be an element of H of P. And of course, it holds true also for the semigroup generated by S. A trickier part is to prove that the genus is the right one. In this case, we use the theory of a priori sets, which are fundamental tools in the theory of numerical semigroups. Now, the a priori set of a semigroup H at a non-zero non-gap N is the set of non-gaps X such that X minus N is a gap. And it's a very powerful tool because if you know for any non-gap and for some non-gap N, the a priori set of H at N, then you can compute the genus of the semigroup, which is, again, in the general setting, which is a very hard task. So we found out that the disjoint union of these ugly sets is actually the a priori set of P at the point at mid the non-gap Q cube. And indeed, you can check that all the properties holds true. Therefore, we have our statement. Now, as I told you before, if you know the Weierstrass semigroup at a point P, then you can sometimes get an improvement on the Goppas bound. So if the Weierstrass semigroup at the point P is this one, rho 0, and so on, then you can construct the one-point AG codes, actually a dual code, you see C omega, with divisor G given by rho LP, namely the multiplicity of P has to be the Lth non-zero, the Lth non-gap of the Weierstrass semigroup. Then you can compute this quantity here, mu m, which is the size of the number of couples such that you can obtain this non-gap as the sum of two non-gaps. And you have that this quantity here, namely the minimum of all this quantity nu m as m goes from L onwards, provide a lower bound on the minimum distance. And therefore, of course, the maximum between this new bound and the previous bound, the Goppas bound, is a lower bound on the minimum distance. And this is called the Feng-Rao design minimum distance. And it can provide an improvement on the Goppas bound. And we actually provided in our work parameters for some particular case, and it turns out that this is, in most of the cases, actually an improvement on the Feng-Rao, on the Koppas bound. Okay, that's all I wanted to say. Thank you for your attention.